Great. So let's talk about find S, which is the first algorithm that we're going to learn for concept learning. So find S's intuition is very simple. It's going to find the most specific hypothesis that's going to cover all of the positive examples. So we're going to start with the most specific hypothesis before we see any data. And because we haven't seen any data, the most specific concept would be to reject all of the data points. So basically, it's going to start with a hypothesis, H0, that requires nulls for all 6 of the attributes. Okay? This basically translates to saying, I don't prefer any drink at all. Okay? And what we're going to do is we're going to iteratively go through the data set and find drinks that the target concept says, basically our friend says that they like to drink. Okay, if they like to drink that, it's a positive instance, then our specific hypothesis of H0 doesn't hold anymore, and we need to, generalize it a little bit. Okay, we're going to do it in such a way that it minimally generalizes to satisfy the input instance. So we're going to keep the amount of items that we feel are going to be positive, that we want H to declare as positive, as small as possible. Okay, so for each positive training instance after we initialize our H0 to what we saw up there before, is we're going to look at each positive instance and then go through all of the attributes, right? So we're going to go through the attributes one by one. So the first dimension of X to the sixth dimension of X, and we're going to check whether that particular example is satisfied by the current hypothesis H. If it is, then we don't have to do anything. It's already consistent. Our H is already consistent with the data. If it isn't, then it's inconsistent, and we would like to make it consistent so as to have the same output as the target function. Okay, then we're going to replace our constraint in the hypothesis by the next most general constraint, more general constraint that minimally satisfies that data item. Okay, and you'll notice here it doesn't have any thing that it needs to do for the negative example. So I'm going to ask you, why is that the case? Okay, and then later on, after we finish going through all of the different instances, we're going to output the hypothesis that we want to share with the agent executing our program. Okay, so we're going to look through this and understand why proposition 1 is actually true. So proposition 1 states specifically that the hypothesis that is being considered at a particular time step in D for the data is consistent, okay, with the target function, meaning that for every positive examples, it's going to output a positive value, so F and H agree. And for every negative training instance, meaning that F is negative, H doesn't satisfy it. That means it's also going to return a negative. So meaning that H and F approximate each other perfectly on the data set that we are given. Okay, so let's step through this algorithm and see how it works. So down below, we have two charts here, one of instance X, this is the instance space, and one of the hypothesis space. And I'm going to show you what they mean in a little bit more detail. Let's see what we can zoom here a little bit. Okay, so I'm just going to check that that worked. Give me a second here. Okay. So on the left-hand side, we have particular instances, and we're going to start with X1 here. So this is a case where the target concept says, yes, I like this drink, and it is coffee with evaporated milk with no sugar and iced, thick, and to drink here. So we're just going to indicate it in our instance space as X1. Okay, so here we go. We'll give it a positive example there. All right, and so it's just somewhere in our X space. And what we're going to do is when we encounter this first positive example, we have to update. So we're going from our current hypothesis that says reject everything, and we're going to say, oh, you know what? It's not true that you don't like any drinks at all. We know at least one drink that you like, and it's exactly the data item that we passed in. Okay, so I'm going to move from this more specific hypothesis and take this partial ordering edge and say uh, minimally to minimally change H0, I have to choose one of the attributes and make it specific. Sorry, to choose all 6 of the attributes and make it more specific. So I'm enumerating one drink here. Okay, then the next step, what we're going to do is do the same for the next round. Okay, so we're going to look at X2. So this is our second training example. This is also a positive example. So it does mean that we have to update if our hypothesis doesn't satisfy is not consistent with the actual label, right? So if you look at our H1, it's too specific. It doesn't handle this case because this particular dimension, our third dimension, which represents sugar, is different, right? So if we want to make it encompass that one and be consistent with the data set after 2 rounds, we have to generalize it, right? So we're going to take our kosong here, which means 0, and we're going to say, actually, we don't care about the amount of sugar in our drink. We think that you're okay with both, okay? So that's how we've updated it here, okay? So now we're going to look at X3. Okay, this is our first negative example. And here we're given all of this information about how this person doesn't like a particular type of tea that's black. Okay. And so even though it's a negative example, as we saw in the algorithm before, we don't need to do anything because we are basically saying that this is the accepting border, okay, that anything with this characteristic is considered a positive example. Anything beyond that is a negative example. So clearly all of the other drinks are outside of that, so we don't have to do anything here. Okay, and so right now with H2 and H3, basically we have this oval, which is encompassing both X2 and X1. Okay, so that's great here. We have X3, and we can annotate that also on this diagram as being over here, X3 being a negative example. Okay, and since it's outside of the oval, we don't have to do any updates, so we can just represent that the orange and the green ovals are in the same place. We didn't have to do any updates for the negative examples. Okay, and for our final update, we need to do an update because this is again a positive example, and a couple things have changed here. So you can see here that this one is weak, and I think this one should be dabao. Okay, so we have to change both of these. This is actually supposed to be like this. Okay, and therefore we have to generalize these 2 constraints. And when we do that, we've moved farther down. We've had to change 2 attributes. So we've gone in this partial ordering lattice 2 steps down, and we encompassed a larger, we're admitting a larger set of instances as positive in this case. All right, so hopefully you understand that step through. Basically what's happening is we are trying to move through this lattice over here, okay, in such a way to make sure that we're consistent with all of the data items that we've seen up to this point, okay? And we're not going to go beyond that. So we're trying to find the minimal amount of positive examples that we need to constrain and say is consistent with our data set. Okay, so this is interesting because if we assume that our target concept, that means the learner, the target concept, meaning the person who is expressing whether they like to drink or not, their concept of what they like is actually embodied in this conjunctive hypothesis space, meaning it's in our script H, then using concept learning by the fineness method will be consistent, okay, up to the mth round. So if we go through all m data points in our data set, we are going to end up with a hypothesis that is consistent on all of the data that the system was exposed to, okay? So you can reason this out, okay, because If it's not coverable by the hypothesis, then we're out of luck. Okay, so if F is not a member of the hypothesis set, we won't be able to necessarily cover it. But we've shown at every step, okay, through all of the M steps, meaning all of the individual data points, every time we update or go through a variable, an input instance, we are either going to update or keep our hypothesis the same, right? And when we're doing that, we're going to guarantee that we are consistent, right? Because every time we need to update, it's because we got a positive example and we needed to generalize by stepping through the lattice. Okay, every time we got a negative example, we don't have it to do anything because the hypotheses are already covering all of the negative examples by default by starting with the most specific hypothesis. Okay, so we've learned FindS, which is our first algorithm for dealing with concept space, but it does have some limitations as a toy algorithm. One important caveat of FindS is you can't tell whether we've actually learned the target concept or not. Okay, we can only say that on this case that it has converged to a hypothesis within script H that is consistent with the data set. So that means for all x that is inside of my data set, f of x does agree with h of x. So we'll say it the other way around. H of x implies that f of x is true, okay? So it's consistent. However, we don't want to just think about it this way. We would like to have some idea of whether the true identity of the concept, even in unobserved examples, is actually correct or not. So we don't have that capability yet, so we'll talk about that later. Okay. Another key limitation is we can't tell when training examples are inconsistent. Okay, this is a very important problem. In a lot of data science and machine learning, we have instances that are noise, right? They may be annotated incorrectly, or perhaps the measurement of certain attributes is incorrect. So we could get examples in our data set that have the wrong label. Okay, if that's the case, then we would have some inconsistency, and then FindS may not actually return the right thing. Okay, so those types of inconsistencies can mislead this algorithm tremendously because, for example, it ignores negative examples. So if the negative examples were actually supposed to be positive, then there should have been some generalization taken, which wasn't actually done. Okay, now, it does pick a maximally specific H because every turn that we update, we're just trying to do the minimal amount of change to satisfy the consistency of the data, right? So every move, every iteration, we're guaranteeing that we have a maximally specific H, okay? But the problem is there could be many different versions of this. So for example, if we were exposed to the data set in a different order, there might be a different way that we could maximally specify a consistent hypothesis that's still very specific, okay? So that type of ordering of the data set is making different hypotheses come out at the end of the execution of FindS. So we might want to have some guarantees to figure out how to pick from among a set of consistent hypotheses, because there may be more than one, okay? Or at least to enumerate that entire set rather than just pick one of them to return. So we're going to try to address some of these issues in the next post lecture, where we're going to talk about the candidate elimination algorithm. So we'll see you then.